Okay, let's dive into this. Have you ever just looked up at the night sky and wondered what you're really missing? Well, it turns out almost everything. Welcome to a journey through the hidden colors of the cosmos, where we're going to see why one single view is never, ever the whole story. So take a look at this. This is the exact same galaxy, but it looks completely different in each image. I mean, one's this vibrant puff of gas against that deep black space. Another is a ghostly whisper. And then there's the swirl of stars we kind of recognize. So what's the deal? How can that be? This is the central mystery we're going to unravel today. First up, let's look at this galaxy in radio waves. Now, this isn't sound, it's a type of light with super long wavelengths. And these waves are amazing because they can slice right through all that thick cosmic dust that usually hides what's going on, giving us this incredible peek deep into a galaxy's structure, the raw fuel for making new stars. Okay, now let's switch our view to infrared. Think of this as the universe's heat signature. This light, totally invisible to our eyes, shows us the gentle glow of cool dust and, maybe my favorite part, the warm nurseries where new stars are literally being born, all tucked away inside these dense clouds. It's the universe's hidden warmth. And here we go, the one we all know, visible light. This is the tiny, beautiful little sliver of reality that our eyes are actually built to see. This is where we see the familiar light from billions of stars, kind of like the ones we see in our own night sky. It's absolutely gorgeous for sure, but as we're finding out, it is just one piece of a much, much bigger puzzle. And finally, the really high energy stuff, the X-ray view. Whoa, these photons are just packed with energy, and they come from the most violent events in the universe. We're talking superheated gas spiraling into a black hole, or the shockwave from a star that just exploded. This view shows us the galaxy's most dramatic, high-octane secrets. So if all this light is out there, why can't our eyes just see it? Well, the problem isn't our eyes, it's what's sitting right above our heads, our own atmosphere. It acts like a giant planetary filter, and it's blocking almost all of the good stuff. Yeah, this side really says it all. Look at this huge range of light in the universe. Our atmosphere, the thing that keeps us alive, is also a cosmic gatekeeper. It is almost completely opaque to most of this information. It blocks nearly all gamma rays, X-rays, and most of the ultraviolet and infrared light from ever reaching the ground. But here's the thing about astronomers. They're clever. If the front door is locked, you find an open window. And it turns out, Earth's atmosphere leaves a couple of key windows cracked open for us to peek through. So from right here on the ground, we have two main windows to the cosmos. First is the one we all know, the optical window, which lets in the visible light our eyes are built for. But the second one, the radio window, is way wider and, honestly, in many ways, a lot more powerful. It lets us map out the hidden structure of our own galaxy without ever leaving home. But there's a catch with radio waves. There's always a catch, right? It's all about something called angular resolution, which is just a fancy way of saying how sharp the image is. It's like the megapixels on your camera. And here's the rule. The longer the wavelength of light, and radio waves are super long, the bigger your telescope needs to be to get a clear picture. And just how big are we talking? Well, to get the same sharpness with a radio telescope that a decent optical telescope gets easily, a single radio dish would need to be, wait for it, 13 kilometers wide. That's almost 8 miles across. So yeah, building a single dish that big is not going to happen. So astronomers came up with this brilliant workaround called interferometry. Instead of building one impossibly huge telescope, they just use a whole bunch of smaller ones spread out over a large area. They collect the signals from each dish and then, with some computer magic, combine the data to create a virtual telescope that's as big as the distance between the dishes. It is so powerful, it's how the Event Horizon Telescope took that first ever picture of a black hole, by basically turning the entire planet into one giant telescope. Okay, but what about all that other light? The infrared, the X-rays, the stuff our atmosphere blocks completely. To see that, there's really only one choice. We have to go above it. We have to go to space. But as soon as you get into space, a whole new set of problems pops up. For an infrared telescope, which, remember, sees heat, the biggest enemy is itself. The telescope is warm, so it glows brightly in the very same infrared light it's trying to see from across the universe. It's like trying to listen for a whisper while you're shouting. So the only way to get around this is to make the telescope colder than the faint, distant things it's trying to look at. The solution sounds simple, but it's an incredible engineering feat. You have to cool the entire observatory down to unbelievably low temperatures. And we are talking seriously, ridiculously cold. To get rid of that thermal noise, telescopes like the Spitzer Space Telescope were cooled with liquid helium all the way down to about 4 Kelvin. That is just a few degrees above absolute zero, the coldest temperature possible in the universe. To put that in perspective, that's way colder than the surface of Pluto. Now, X-rays have a totally different problem. These things are like little bullets of energy. They don't behave like visible light. If you try to bounce them off a normal mirror, they don't reflect. They just punch right through it. So how on earth do you focus them? The answer is just genius. You don't let the X-rays hit the mirror head-on. Instead, you use these special barrel-shaped mirrors. The X-rays come in at a super shallow angle, less than 2 degrees, and just skip off the surface. It's exactly like skipping a stone across a lake. It's this clever little cosmic trick that lets us focus the universe's most energetic light. Escaping the atmosphere gives us this absolutely unmatched view of the cosmos. But that incredible clarity, well, it comes at a very, very steep price. So let's talk about the reality check of putting telescopes in space. The single biggest disadvantage? You guessed it, money. This chart says it all. A space telescope can cost anywhere from 100 to 1,000 times more than a ground-based telescope of a similar size. That's to build it, to launch it, and to operate it. It is an astronomical investment for an astronomical view. There are also some common myths. For instance, you might think a space telescope can just stare at an object all day, every day. But for a telescope in low Earth orbit, like Hubble, our own planet gets in the way. The Earth blocks its view for about 45 minutes out of every 90-minute orbit. And here's another one, that the sky in space is perfectly pitch black. I mean, it is incredibly dark, for sure, but it's not pure black. There's still this faint background glow from sunlight scattering off tiny dust particles between the planets, and the combined light of billions of distant, faraway galaxies. So, after all the challenges, all the incredible costs, and all the brilliant engineering, what do we actually get? Well, by putting all of these different pieces of the puzzle together, we finally get to see the universe in all of its incredible, hidden glory. And this, right here, is the big takeaway. Every single wavelength of light tells a different part of the cosmic story. Visible light shows us the stars. Infrared uncovers the hidden dust and places where stars are born. Radio waves trace the grand, sweeping structure of a galaxy. And X-rays pinpoint the most violent, energetic things happening out there. You have to see in all these colors to get the full picture. It's only by combining all of these invisible colors that we can start to see the universe as it truly is. And it makes you wonder, doesn't it? If this is what we've managed to uncover just by finding new ways to look at light, what other cosmic secrets are still out there, hiding in plain sight, just waiting for us to invent a completely new way to see?